Hello, everyone, and a very warm welcome to Kognito Key. Today, we're taking a fascinating journey under the hood to decode the actual language of the CPU. We're going to break down instruction formats and sequencing so we can finally understand how your computer truly thinks.
Okay, let's dive right into this. You might be wondering, how does a computer actually know what you want it to do? You click a mouse, you press a key on your keyboard, but how does that human intent actually translate into a physical machine action? Well, it all comes down to instructions. Every single program running on your device is, at its core, just a massive, microscopic list of incredibly precise commands.
To make sense of this, think of a basic instruction, kind of like a simple sentence. First up, we have the opcode. You can think of this as the verb of our sentence. It tells the processor exactly what action to take, like adding numbers or moving data around. Second, we have the operands. These are our nouns. They pinpoint the actual data that the opcode is going to act upon, whether that data is sitting out in memory, stored right inside a processor register, or just provided directly as an immediate value. So the crucial point here is that no matter how incredibly complex your software seems on the surface, the whole shebang literally boils down to just four main types of instructions. We've got data transfer, which simply moves information between memory and processor registers, then arithmetic and logical operations. These are the ALU tasks that actually crunch the numbers. Next is sequencing control, like branching, which changes the flow of the program. And finally, I/O transfer, which handles data moving between the internal system and external storage. Now, to describe exactly how data moves during these operations, computer scientists use something called register transfer notation, or RTN for short. If you look at the equation, notice that arrow pointing to the left? The rule is actually really straightforward. The CPU evaluates everything on the right-hand side and then transfers that result to the destination on the left. So in this case, it adds the values inside registers R3 and R2, and then it completely overwrites whatever was previously sitting in R4 with that brand new total. But let's be real for a second, reading brackets and arrows all day, it isn't very friendly for programmers. So we transition over to assembly language notation. Assembly uses easy-to-read mnemonics, basically simple, memorable words like add, load, or store. That exact same addition operation we just looked at is now beautifully simplified to just add R4, R3, R2. Much better, right? Now, what's really interesting about this next concept is the massive shift it represents in computer history. On one side, we have CISC, complex instruction set computers. These were huge in the 1970s, using heavy, multi-word complex instructions like a general move command for transferring data directly from one memory spot to another. Contrast that with RISC, reduced instruction set computers, which is modern architecture. RISC is highly streamlined. Every single instruction fits perfectly into a single word. It uses a very strict load and store method for memory, and those ALU operations, they only ever happen directly in the registers. This incredible efficiency is exactly why RISC architecture is powering almost every smartphone sitting in our pockets today. All right, let's move on to the main event, the execution cycle. How does the processor actually pull off these commands? Well, it sequences and executes them in two distinct sequential steps. Step 1 is the instruction fetch. This is where the CPU checks the program counter, which is a special register that holds the exact address of the very next instruction to grab. Then, in Step 2, instruction execution, the command is loaded into the instruction register, the CPU examines it, fetches any needed operands, and physically performs the operation. Now, normally a processor just moves straight down a list of instructions. We call this straight-line sequencing. It's the standard way things run in increasing order of memory addresses. Every time an instruction is fetched, the program counter automatically increments itself by the word length. So it calmly updates to point to the very next consecutive step. Just step 1, step 2, step 3, marching right down the line. But think about it. What if we need to repeat a step? Writing the exact same instruction 100 times in a straight line would be terribly inefficient. And this brilliantly illustrates the power of branching instructions. Branching allows us to break that straight line sequencing so we can create dynamic loops. For example, if our instruction says branch if R2 is greater than 0 and that condition is actually true, the CPU loads a brand new branch target address directly into the program counter. That sends the program right back to the top of the loop, and it will keep looping until that condition finally becomes false. It's honestly truly elegant how these simple, fundamental rules of fetching, executing, and branching combine to run all the intricate software we rely on every single day.
The underlying language of the CPU is an absolute masterpiece of logic. But it leaves you wondering, as we push further into the era of quantum computing and advanced neural networks, will this basic instruction format survive? Or are we on the brink of an entirely new machine language? Thank you so much for joining me today on Kognito Key. If you enjoyed diving into this, please make sure to subscribe to the channel and absolutely like and share this explainer with your fellow tech enthusiasts. Keep learning, and I will see you in the next one.